So we know everything there is to know about bond polarity, which just refers to the degree of sharing between two different atoms. And that if the atoms are the same, like hydrogen and hydrogen, the electrons are shared the same. The atoms have the same electronegativity, the same attraction for the shared electrons. That does not create any region of charge if the electrons are just shared right in the middle of the two atoms. When you have atoms with different electronegativities, the electrons are drawn or pulled closer to the atom with a higher electronegativity, as was the case with hydrogen and fluorine. The bond was polar, creating regions of charge, and because that's the only bond in the molecule, it leaves the whole molecule with regions of positive and negative charge. That's what it means to be a polar molecule, that there are regions in the entire molecule that are positive and negative. Well, in the last segment, we looked at molecules that might have polar bonds, but if those polar bonds are arranged at equal angles around the outside, you can have equal poles at equal angles and they cancel. And then you're left with a molecule that's overall nonpolar, even though each individual bond might be polar, as was the case with carbon dioxide. The carbon-oxygen bond is polar, but because of the way they're arranged in the carbon dioxide molecule at this linear structure, the atoms are pulling with the same force, but at the same angle. Equal angles, same force. It's like tug of wars where everyone is pulling at equal angles with the exact same force. And if the flag then is represented by the electrons on the central atom, the flag's not going anywhere. And neither are the electrons. If those poles cancel out because they're arranged at equal angles, you really don't get a region of charge. And so we said linear, trigonal, planar, and tetrahedron were the shapes that have equal angles. So in order to be a nonpolar molecule, nonpolar molecules need equal poles, meaning that the atoms around the outside are the same, so that they have the same electronegativity and they're pulling on the electrons at the same force. I need equal poles at equal angles. So I gotta have all the atoms on the outside the same, and they have to be pulling at equal angles, which is what happens with these three shapes. What about the other shapes? What about the polar molecule? Okay, so think about a tetrahedron. Like, for example, carbon tetrafluoride is a good one. We can draw carbon and 4 valence electrons, and let's put on some fluorines with 7. Then I can connect the dots. And hopefully now drawing these structures is becoming somewhat manageable, and that you're starting to realize there's just not that many atoms to pick from. When I'm only dealing with the non-metals on the periodic table, and this structure would be the same if I had any halogen around the outside, or I could have any member of the carbon family on the inside. If the atoms had the same number of valence electrons, they're going to give me the same dot structure. Okay, so here's carbon tetrachloride, or tetrafluoride, I should say. If I look at the periodic table between carbon and fluorine, fluorine has a higher electronegativity. I mean, it's the highest on the whole periodic table, but I also know that it's got more electrons, it's got more protons, so there's a stronger attractive force within the fluorine atom, and it's got more valence electrons, so it's closer to getting that octet. Okay, so here's what happens then. In this structure, I'm going to have a pole. The electrons in this bond are not shared equally. It's a polar bond. The electrons are going to be pulled up toward the fluorine. But look at the way they're arranged around the center carbon. I mean, there might be a little pull up toward the top fluorine, but then there's a pull on the bottom, and they cancel. There's a pull, and there's a pull. It's equal pulls because it's all fluorine around the outside, equal pulls at equal angles. So they cancel. And you end up with a tetrahedral structure, 4 electron groups, all 4 are bonding groups, but the little poles cancel at equal angles, and it's overall a nonpolar molecule. Let's put that in here. This is a nonpolar molecule. Even though each individual bond is polar, the carbon-fluorine bond is polar. The electrons are not shared equally, but it's because of the arrangement of those polar bonds around the center that they cancel. And overall, I don't have a substantial region of charge. But now look at the water molecule. So you draw a water molecule. I mean, all of these are going to start by drawing the Lewis structure because I want to know how many electron groups are on the center atom and how are they arranged on the center atom. Okay, so I've got my 2 bonding regions and my 2 lone pairs, my 2 non-bonding electron groups. Around the center oxygen, there are 4 groups of electrons. 4 groups of electrons makes me think tetrahedron, which now, again, we don't draw our dot structures in 3D just because that would be a little tricky. But when I think of a tetrahedron, I'm really picturing this little rocket ship, right? If I try to kind of draw it in 3 dimensions, and it's not flat. Here's my tetrahedron where the angles are bigger than 90, even though my drawing kind of looks like 90-degree angles. Well, in real life, if we go in 3 dimensions, we can get those angles farther than 90 degrees, almost 110 degrees apart. But they are all equal angles around the center. They're all about 109.5 degrees. Okay, so 4 electron regions. Here's my 4 regions. There's the 2 bonding groups, and then there's the 2 lone pairs. That makes me think tetrahedron, but 2 of those groups aren't really atoms. So if I take my tetrahedron and I pop off 2 atoms to say, like, yeah, they're not really atoms, they're now lone pairs, well, it leaves me with something that's maybe kind of like this, where here's a lone pair, and maybe over here was a lone pair. Oh, so it's still 4 electron groups. Makes me think tetrahedron, but 2 of them aren't really atoms anymore. And so the angles are pretty similar to a tetrahedron. It's just that what I'm left with is bent. Remember that bent structure? Yeah, I mean, look at the blue molecule. It's bent. It's not linear. Linear is if I only had 2 electron groups and they were bonding groups. Well, now I've really got 4, which causes more repulsion. So the angles are less than 180. I've got 4 groups of repulsion rather than 2. Okay, so look what happens then. If I check out the electronegativity of oxygen versus hydrogen. Okay, so on my periodic table, I see that oxygen is right next to fluorine, the big man. Yeah, oxygen's still a pretty small atom with lots of attraction, and it still has a pretty high electronegativity. It's got 6 valence electrons. He wants 8. Oxygen definitely has a higher electronegativity than hydrogen, which is what they're trying to show here then, that the electrons shared in the bond between oxygen and hydrogen are not shared equally. It will be a polar bond. The bond between hydrogen and oxygen is polar, with the electrons being pulled toward the oxygen. He's got the higher electronegativity. Okay, so the bonds are polar, the electrons are being pulled toward the oxygen, so there's kind of this net pull for all the electrons in those bonds to be drawn up toward the oxygen, which then creates a region of charge. Oh, which is kind of what they're trying to show on this electrostatic diagram, that when the electrons are being pulled up toward the oxygen, that oxygen atom is going to become partially negative. We could put in a little partially negative. We could put one in here, partially negative. Which then, if the electrons are hanging out closer to the oxygen, that means they're not hanging out by the hydrogen, so the hydrogens become partially positive. Partially positive. And that's kind of, again, what they're trying to show with that blue and red bubbly looking thing at the end, that the oxygen region is charged slightly negative and the hydrogen region is charged slightly positive. When there's regions of charge, that's a polar molecule now. The key is that I don't have poles here that cancel each other out. I don't have a shape that gives me that nice symmetrical angle around the outside. And if I had like polar bonds, like maybe I had a pole here, but I don't have an atom up here to balance. And I could have a pole here, but again, there's no atom here to balance. So even though I have equal poles, I might not have equal angles. They're not arranged evenly around the center so that they would cancel. Now that's what happens in the linear structure, where linear molecules only have two atoms around the center, kind of like the water molecule did. But then the linear molecule has the nice 180-degree angles. It's an equal angle all around the center, so those little poles can cancel. They're pulling in the same direction. That's not what's going to happen in a bent structure. I don't have an equal arrangement around the center. I don't have equal poles at equal angles. And so you're left with a shape then that will have a region of positive charge and negative charge. That, my friends, is a polar molecule. So some examples. Question 19 says to draw the structure of sulfur dichloride. We're going to use the VSEPR theory to draw the model that shows the shape, its polarity, and it does talk about electronegativity differences. You don't even need that. All we need is a periodic table, and we can predict electronegativities. And so this is really similar to the last example, but watch what happens. So we would draw the structure. So I draw my sulfur, 6 valence electrons, 2, 3, 4, 5, 6. Perfect, I have 2 chlorines. Chlorine, I can hook them on. 5, 6. Chlorine, 1, 2, 3, 4, 5, 6, 7. Connect the dots, there she is. Okay, so here's what I could be asked to do on a summative assessment, like bring it all together. First they might say, draw the electron dot structure. Well, there it is. There's the electron dot structure. Next they might say, describe the shape of this molecule. What is the VSEPR geometry? For that, I want to count all the electron groups around the center atom. Oh, what do you know? 1, 2, 3, 4. There's 4 of them again. 4 shapes in my head is making me think tetrahedron. Tetrahedral rocket ship. 1 atom in the middle. 4 atoms in 3 dimensions around the outside. So they might say, what is the shape of this thing? On my head, 4 electron groups, as far apart as possible, tetrahedron. But then I'm picturing, well, 2 of those spots aren't really atoms. So if I pop off 2, and it can be any 2 atoms, but what I'm left with is bent. So again, I'm kind of picturing that up in this top spot is an electron pair, and in this spot is an electron pair. The sucker is left bent. Now another question they might ask you is to describe the angles. Now, you do not need to memorize the 109.5 for a tetrahedron. But what if the question just said something like this? Are the angles greater than, less than, or equal? Whoopsies, or. We're not mining an or. Greater than, less than, or equal to 180. What if the question just said that? Are they greater than, less than, or equal to 180? I've got one central atom and I got two atoms around the outside. 180 would be linear, right? Well, we know linear is 180. Well, we have to just know here that, whoa, wait a second. Even though this formula might look something like, my CO2, where there's one atom in the middle and there's two atoms on the outside. Oh, but once I drew this, I noticed that there's actually not just the two bonding groups, but there's also two more lone pairs. There's 4 electron groups on the center. That creates more repulsion. Oh, yeah, those other 2 electron groups, they're going to make the angles less than 180. You don't have to memorize that it's 109.5. I just want you to know that there's more repulsion when I have more and more electron groups, and that's going to make the angle smaller. I've got 4 groups that are all repelling around the center atom, even though only 2 of them are actually bonds. But it makes angles that are less than 180. This guy right in here is definitely not a linear angle. All right, then what else might they ask me on a summative? They might ask me about the bond polarity. They might say, is the sulfur-chlorine bond ionic, polar, covalent, or non-polar covalent? They could ask me something like that. What about the individual bond? Is the bond polar covalent, non-polar covalent, or ionic? When I can say right away, I know it's not ionic, because that's got to be metal, non-metal. Well, sulfur and chlorine are both non-metals. They're different non-metals, so I know it's going to be a polar covalent bond. They're going to share, but not equally. Okay, that's cool. If you've got different non-metals, they're most likely going to have different electronegativities, and they will not share the electrons equally. They might ask me to indicate the bond polarity or describe the bond polarity. Describe the bond polarity. And we'd say, okay, well, if I have this sulfur-chlorine bond, and I'm going to look at the periodic table. Okay, so sulfur and chlorine are right next to each other. They're in the 3rd row or the 3rd energy level going across. But going across, I know that chlorine has an extra proton, an extra electron. Chlorine is going to have a higher electronegativity. It's got 7 valence electrons and really wants that one more. With chlorine having a higher electronegativity, then the electrons in this bond will be drawn closer to the chlorine atom, and the chlorine side should be partially negative, and the sulfur partially positive. There's the bond polarity. Or they might say, like, which atom would be partially positive, or which atom would be partially negative? The atom with a higher electronegativity gets the partial negative. Now, finally, they might ask me about the molecular geometry. Maybe they'd say, like, is this a polar or non-polar molecule? Is this a polar or a non-polar molecule? Well, now I'm going to say, okay, I've got polar bonds, so I know there's going to be a pull for the electrons to be out closer to the chlorines. But because I don't have any other atoms to balance those poles, I might have equal poles, but they're not at equal angles. So that leaves this as a polar molecule. Holy cow, that's a lot. But that's what you could see on the summative. They could give you a structure and have you draw it and answer all these kinds of questions in reference to that initial molecule that you drew. Okay, now in a nutshell, do you want to know how to make this polar, non-polar molecule stuff kind of easy? So check this out. Originally we said that here are the three shapes that do have an equal arrangement around the center. The linear, the trigonal plane, or the tetrahedron. As long as the atoms on the outside are the same, then I'll have equal poles at equal angles. And all those little poles will cancel. These are your non-polar molecules, as long as the atoms on the outside are the same. Well, what shapes are left? Bent. So it could be this bent, where you've got 3 electron groups. 2 of them are bonds, and then the third spot is a lone pair. You could have the bent that we just drew, where you've got 1 atom in the middle, 2 atoms on the outside, but maybe 2 lone pairs. It's just like a little bit more bent. And the first bent that I drew, the angles are close to 120. And now there's just a little more repulsion and the angles are close to 109. Check out the bends. And then the other structure that's missing yet is the trigonal pyramid, where you've got the 3 atoms and the 4th spot is a lone pair. The trigonal pyramid. Look at these 3 structures. And what do you see that is common about all of the 3? Are you thinking in your head lone pairs? Yes. All of these structures are polar. These are the polar molecules. Where can I write that? Polar molecules. These are the polar shapes. So if you draw your initial structure and it comes out to be bent or trigonal pyramid, it's a polar molecule. Whenever you have lone pairs on the central atom, it represents a spot where you could have another bond and you don't. And so what you're left with is then an arrangement that does not give you equal angles around the center. If I had all 3 atoms, I would have the trigonal planar. If I had all 4 atoms, I would have the tetrahedron. But if I have lone pairs, I'm missing some atoms. And then what you're left with will not be an equal arrangement around the center, and it will always be a polar molecule. So you draw the structure. If you got lone pairs on the central atom, you've got a polar molecule. If you don't have lone pairs, it's a non-polar molecule, as long as the atoms on the outside are all the same.